Diffusion Mobile, quality e-learning experience on the go.
Welcome to Diffusion Mobile e-learning clinic. My name is Sonia Lalwa and you're welcome, and this is a chemistry course. You're welcome to the chemistry course. In this lesson on the kinetic theory of matter, we'll be looking at the kinetic theory. We'll talk about the states and change of state of matter. We'll look at the phenomena supporting the kinetic theory. We'll talk about the kinetic theory of gases, and we'll consider Boyle's law, the Charles law, the general gas equation, Dalton's law of partial pressure, ideal gas equation, Avogadro's hypothesis, relative vapor density, and the Graham's law of diffusion of gases. Alright, let's start. The kinetic theory. What does the kinetic theory mean? When we talk about kinetics, we talk about motion, we talk about movement. It is assumed that it is believed that in gases, in substances, there is always energy possessed in the substance lying down there, and this energy makes the molecules of the substance to be in constant motion. So one of the part of the kinetic theory states that every atoms of a body are always in constant motion. We know that matter exists in different states. Three different states we know. These are the liquid states, the solid states, the liquid states, and the gaseous states, that is the gas. In the solid states, the matter actually, we've talked about this before. In the solid states, the matter actually occupies a fixed volume and maintains a fixed shape. In the liquid state, it bends into all the shapes, but maintains its original volume. But in the gas, it neither keeps its volume nor maintains its shape. When we talk about change of state, that is conversion of a substance from the solid state to the liquid state, or from the liquid state to the gas state, or from the gas state to the liquid state, or the liquid state to the gas state. So how do these things occur? There are several levels at which it can occur. We have what we call evaporation. Evaporation is the conversion of liquid to gas. Is the conversion of liquid to gas before the boiling point temperature of that particular substance. So for example, I take water, I pour it on the table, and I leave it there. I don't put any heat, I don't do anything. After some time, you come back there, you notice it is dried. You wash your clothes, you hang them in your room, because you don't want thieves to steal them from the line outside. By the next day, you see that it is almost completely dry, or probably even completely dry. You keep your room, you mop the floor of your room, you turn on the fans, and in a few minutes, it is completely dry. The room temperature did not reach the boiling temperature of water, but you were able to evaporate or vaporize the liquid. Another point is described as boiling. Boiling is the conversion of a liquid to gas by it increasing the temperature of the liquid such that it hits the liquid till the point that the liquid begins to boil. When the liquid boils, then vaporization occurs. Of course, this is conversion of liquid to gas. So basically, both of them are kept under what is known as vaporization. Converting a liquid to gas is called vaporization. Of course, converting a gas back to liquid, so liquid to gas, L to G, is that. Now, converting a gas to liquid is known as condensing or condensation. Is known as condensation. You are cooling the liquid, the gas, and converting it to liquid. Of course, we also have what we know from the liquid to solid. Yes, liquid to solid is described as freezing, while solid to liquid is described as melting. Of course, I know you're familiar with many of these terms. Let's quickly Okay, before we go any further, let's take this short break. In a few seconds, some questions will be displayed on your screen. We want to see how much of what has been taught so far in this lesson you have understood. Please answer these questions and we'll get back to you in a few. Thank you. Okay, welcome back. We've considered the kinetic theory, a brief talk about the kinetic theory, and we also talked about the state and change of state of matter. So let's quickly look at phenomena supporting the kinetic theory. We have claimed that there are certain conditions this kinetic theory exists. So what evidences do we have to prove it? Well, the first evidence we do use to prove the kinetic theory is the Brownian motion. The Brownian motion. A particular scientist known as Brown conducted an experiment, and he observed that there was a kind of movement, random movement within the atoms of within a particular compound, a particular substance, and he noticed that the atoms were moving, they were vibrating. So this particular motion is described as the Brownian motion, and this motion is created due to the possession of kinetic energy by the atoms of the substance. Another thing we use to discover to prove it, another phenomenon, is diffusion. Diffusion. In diffusion, you have your perfume and you spray it, or you have your air spray, your what's it called? You spray it into your room, and then you discover you're spraying it in a particular small space, and then it expands and occupies the entire room. It diffuses into the entire room. It moves from a region of higher concentration to lower concentration rather to a region. It moves from a region of higher concentration to a region of lower concentration. Also, we have what we describe as osmosis. Osmosis is a different kind of diffusion which occur in a reverse direction. Of course, all these things are evidences to show that the kinetic theory is actually in motion. Okay, let's talk about kinetic theory as regards to gas. In gases, so let's consider the kinetic theory of gases. When we talk about the kinetic theory of gases, it is not just the kinetic theory of matter. It's a little more concise, more restricted to gases. In the kinetic theory of gases, which will be displayed on your screen in a few seconds, we say that, of course, there is energy possessed by the gas molecules, and the gas molecules are in constant motion, only that their motion are in straight lines. They move in straight lines. We also notice that these gas molecules bombard with themselves. They have collisions with themselves, and in these their collisions, the collisions are perfectly elastic. Their collisions are perfectly elastic. Apart from their collision, yes, it is also noted that the actual volume of the gas molecules themselves, since the gas molecules tend to occupy every space you are giving to it, it's assumed that the space the molecules themselves can occupy, if they are compressed completely, is negligible. That is, you can just assume that if it is compressed completely, it will occupy absolutely no space. Also, we believe as well that the coercive force between the molecules, between the atoms of the molecules, is also negligible. That is, there is the kind of attraction that exists between the molecules of the gases is next to zero. That is, the gases are not attracted to each other. That is what that particular law, the theory states. And also, the temperature measured the temperature is also a measure of the kinetic energy possessed by the gas. It's a measure of the kinetic energy possessed by the gas. This kinetic theory of gases finds a lot of application in the explanation of certain laws which we describe as the gas laws. The gas laws. The gas laws are laws which are used to do calculations involving gases, and the very first one of them we'll be talking about today is the Boyle's law. The Boyle's law. The Boyle's law states that at a constant temperature, the pressure possessed by a particular mass of gas is inversely proportional to the volume the gas occupies. So this means that pressure is 1 over V. And that brings us to PV to be a constant. So this is what it is taking. This particular expression shows the Boyle's law. And we can always say our constants by saying P1 V1 equals to P2 V2 and the likes like that. So this is a representation of the Boyle's law. Well, in the course of observing the Boyle's law, the scientists went ahead and started making different experiments trying to see what would happen, and it was discovered that at a particular temperature the volume of gas occupied was at specific volume. And it was observed also that you can actually have supercooled temperatures and volume gases will still exist. So an interpolation was done by a particular scientist known as Kelvin, and he came up with a particular temperature scale which would give you a particular point which, if you can cool a body to that particular temperature, the gas would cease to exist. And this particular temperature is known as the Kelvin's temperature. So the Kelvin temperature, that's 0 Kelvin, it is proportional to minus 273 degrees Celsius. 0 Kelvin is proportional to minus 273 degrees Celsius. Hence, we say 0 degrees Celsius equal to 273.15, actually 273.15 degrees Celsius. So it's equal to 273.15 Kelvin. So this is the Kelvin's temperature scale. Now, Kelvin's temperature scale also, it made us start putting everything into careful notes. And of course, when you work with the gas laws, you will work with the Kelvin temperature scale and not the centigrade or the Fahrenheit temperature scales. When we talk about in this same gas laws, we have a particular gas law that works with temperature change, and that is known as the Charles law. The Charles law states that for a given mass of gas at constant pressure, the volume of the gas is directly proportional to the temperature of the gas. So if you have a particular gas and it has a particular volume, it is directly proportional to the temperature. And if you resolve this, you have V over T, which will be a constant. Hence, we have V1 over T1 equals to V2 over T2. And this is a representation of the Charles law. That's a representation of the Charles law. Now, if you put the Charles law and the Boyle's law and you try to merge them together to form one singular law, you have something that we describe as the general gas equation, which states that P1 V1 over T1 equals P2 V2 over T2. This law can be used once, so long as the mass of the gas remains constant. So long as the mass of the gas remains constant, this law holds. That is, the pressure multiplied by the volume divided by the temperature would give exact replica, will remain constant at every point in time, provided that the mass of the gas remain constant. So the pressure, oftentimes our pressure is measured in Newton per meter square. Our volume is measured in volume squared. Volume squared is measured in meter squared, or usually dm cube, that is decimeter cube. Volume can be measured in meter cube or decimeter cube, and our temperature, of course, is measured in Kelvin. Our temperature is measured in Kelvin. So whatever scale you are given, you must convert to Kelvin before you use it in the general gas equation. Okay, let's talk about Dalton's law of partial pressure. Dalton's law of partial pressure. John Dalton, the scientist, he came up with a principle. He suggested that the amount of pressure exerted by a particular gas or a substance, of a gas, is a summative of all the pressures of each of the components of the mixture all together. That is, in air. In air, we know that we have several different different gases, such as nitrogen, oxygen, carbon dioxide, rare gases, etc. So, what he was suggesting is that the pressure exerted by nitrogen plus the pressure exerted by oxygen plus the pressure exerted by carbon dioxide plus the pressure exerted by the rare gases plus the pressure exerted by other components of the air would be equal to the total amount of pressure exerted by the air. So that is what the Dalton's law of partial pressure states. Also, we have the ideal gas equation. Well, when we talk about the ideal gas, it means we're talking about the standard gas, that is a perfect gas. Although no gas is perfect, but then we have an equation for calculation. We assume that a gas can be perfect for ease in calculations. So we have this formula that says PV equals to nRT, where P is the pressure, V is the volume, N is the number of mole, R is the gas constant, and T is the temperature of the system. So this is used to estimate what the reaction of a particular gas would be. R has several different formulas depending on the nature of the compound of the calculations you are using. It can be, if you are using, we work with pressure as atmosphere, and we also work with pressure as pascals sometimes. So depending on whether we're working with atmosphere or whether we're working with pascals, the gas constant is a constant, of course, and it is 0.082 atmosphere dm cube per Kelvin per mole. So atmosphere dm cube per Kelvin per mole. We do measure in this particular aspect in chemistry, we do measure our volume in dm cube. And also at standard temperature and pressure. What is standard temperature and pressure? Standard temperature and pressure is a normal temperature and normal pressure which we have our atmosphere. Standard pressure is 760 millimeter of mercury, and our standard temperature is 298 Kelvin, which is same thing as 25 degrees Celsius. Of course, 1 mole of any gas at standard temperature and pressure should have a volume, that's volume at STP, should be 22.4 dm cube. 22.4 dm cube. How did they come about with this 22.4 dm cube? That's what brings us to Avogadro's hypothesis. Avogadro's hypothesis. Well, Avogadro made an hypothesis that in every mole of, in every atom, in every mole of a gas or a substance, there is an equal value of number of particles in it. That was his hypothesis. And in this hypothesis, he went to do certain experiments and eventually came up with what is known today as the Avogadro's number. The Avogadro's number represents the number of particles that can be found in an atom, in 1 mole of that particular. Avogadro's number. Avogadro's hypothesis says that 1 mole of a substance is the number of particles in a substance in 1 mole of a substance is the same for every substance. Of course, that 1 mole is in relationship with carbon-12. So we came up with a constant that's number of particles, and that's what we know as the Avogadro's number. We talked about this in the previous lesson, and we gave Avogadro's number to be 6.02 times 10 raised to power 23. That's the Avogadro's number. So that it was gotten from the Avogadro's hypothesis. Let's talk about relative vapor density. When we talk about vapor density, that is the density or intensity of a particular substance. That is when it is the substance, in this case, is a gas. Is a gas because it is gas that exists in the vapor form. And when we talk about density, density is the ratio of mass and the volume occupied by a particular thing. So when we talk about relative vapor density, it means we are comparing vapor density with another kind of density. In this context, vapor density is being compared with air density, the density of the air. Let's talk about relative vapor density. When we talk about density, it is a ratio of the mass and the volume occupied by that particular mass of a substance. In the case of vapor, it means that we're talking about a gaseous substance. So when we're talking about relative density or relative vapor density, it means we are comparing that density of that vapor with the density of another particular gas. In this particular context, we compare the density of vapor with the density of hydrogen gas. So how do we go about this? To calculate relative vapor density, VD, that's relative vapor density, it's calculated as the mass of the given gas divided by the mass of equal volume of hydrogen gas. The mass of the given gas divided by the mass of equal volume of hydrogen gas. So this is how we go ahead to calculate vapor density. Vapor density finds its application a lot in the diffusion of substances. Yes, because Mr. Graham's, the scientist called Graham, he came up with a law which is known as the law of diffusion of gases. He was trying to explain how gases diffuse, and he said when you press a perfume or you press something into the air, an aerospray, it releases gases, and these gases move with a particular speed. He said under the same conditions, that is atmospheric conditions, which is temperature and pressure, under the same atmospheric condition, that is temperature and pressure, the rate of diffusion of a particular gas is inversely proportional to the square root of the vapor density of the density of the gas. The rate of flow of that particular gas, let's call rate of flow R, is inversely proportional to the square root of the density of the gas. Well, we don't usually use this density because we're going to be considering more of relative density, since we cannot actually take an actual density for most of these gas. So we represent that density with D. Now, of course, density is very, very much related to mass. And if you can get equal volume, of course, maybe you have two different substances. You can have your R1. This is supposed to give a constant, so you can have a R1 over R2 to be equal to D2 over D1, and then you find the square root. Of course, you can replace the densities with mass if you have a equal volume, mass in equal volume, and you have your M2 over M1. Of course, your square roots would also be over them. So you can use this formula to calculate the rate at which a particular gas would diffuse in air. So that's the Graham's law of diffusion of gases. Alright, in this particular lesson on the kinetic theory of matter, we talked about the kinetic theory itself. We looked at the state of matter and change of states. We then also spoke about the phenomena supporting the kinetic theory, where we mentioned the Brownian motion. We talked about the diffusion of gases, and also mentioned osmosis. We talked about the kinetic theory of gases, which are three, which states that the conditions for which gases do react, conditions for which gases, this kinetic theory of gases establish the grounds for us to come up with the gas laws, where we come up with Boyle's law, which generalizes P and V, as states that P1 V1 equals P2 V2. We talked about the Child's law, which generalizes P and V and T, and says that when P is constant, of course, V over T is constant. And also we talked about general gas equations, which was generated from the combination of both the Child's and the Boyle's law, which says that P1 V1 over T1 equals P2 V2 over T2. We then talked about the Dalton's laws of partial pressures, which says that if a particular gas, a particular mixture of non-reactable gases is in a place, the amount of pressure, total pressure exerted by the gases, the mixture of the gases, is proportional to, the total pressure exerted by the mixture of gases is equal to the sum of the pressure exerted by each of the gases. We then looked at the Avogadro's hypothesis, where he said that the number of particles in substances are equal. Then we looked at relative vapor density, which is a comparison of the density of a particular vapor or gas in relation to that of hydrogen gas. And then we spoke about the Graham's law of diffusion, which says that the rate of diffusion of a particular gas is inversely proportional to the square root of the density of the gas. Alright, let's take this question before we go. Given mass of a gas occupies 850 centimeter cube at 320 Kelvin and 0.92 times 10 raised to the power 5 Newton per meter square. We're asked to calculate the volume at STP. So to calculate the volume at STP, the first thing to note is what is the temperature. Let's look at our parameters. The given volume, that's V1, is 850 cm cube. Our given temperature, that's T1, is 320 Kelvin. Our given pressure, P1, is 0.92 times 10 raised to the power 5 Newton per meter squared. Alright, we are to look for V2. We know our T2 to be temperature, room temperature, that's 25 degrees C, which is 298 Kelvin. And we also know our pressure, atmospheric pressure, to be 1 atmosphere, which is same thing as 1.01 times 10 raised to the power 5 Newton per meter squared. Alright, then we'll take it and bring up the formula. The formula says P1 V1 over T1 equals P2 V2 over T2. I always like to make my subject of formula. So I have my V2 as my subject of formula. Bring all together, that's P1 V1 T2 divided by P2 T1. Let me put in my values. So from my formula, I put in my values: 0.92 times 10 raised to the power 5 multiplied by 850 multiplied by 298 divided by 1.01 times 10 raised to the power 5 multiplied by 320. When we enter all of this into a calculator, our output result is 660.5 cm cube, and that's how we'll go about calculating for using the general gas equation. In a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson. Please answer them, and if you have any confusion, you can go over the video one more time for better explanation. Thank you.